Okay, did you get it right on the test? We better have gotten this right, or nothing else matters. If we don't have the big picture. We know what? We know how fast a quantity is changing, and we want to know how much of it we have. We know how fast a quantity is changing, and we want to know how much of it we have. So this is the journey we've been on for the last month. Okay? This is the journey we've been on. How can we get an exact accumulation function starting with an exact rate of change function that's changing, a changing rate function, right? And so we saw that this took us a lot of work and a lot of tools and a lot of blood, sweat, and tears to get there, okay? But because of all those, because of our understanding of this process, we earn the right now just to write down the integral. And so given the exact rate, knowing the process that allowed us to build this function, and having put our time in, we have the rate of change. We can just write down the exact function now using the integral notation. We know what it means and where it came from. Okay? So, what we'll do now, we're going to start the reverse process now. You know what? What do you know? You know how much of something you have. And you want to know how fast it's changing. So we're just going to march it on backwards. And here's the deal with this. Because of all the tools and the building blocks that we've laid in the last month, they're already in place, essentially we're going to do this whole thing today. We've got all the tools that we've put in place for going from rate to accumulation. And so we're going to use a lot of those tools again, and we can kind of get the whole idea of the math from the reverse process in one lecture, okay? But again, this is our thing. If we have exact accumulation, we want to just fast track to exact rate of change, knowing what the mechanics of that looks like in between. But in the end, we will not do this today. This is what we'll do after spring break, is talk about what does it look like to just streamline, go straight to exact rate of change, the way that integral allows us to get an exact accumulation function streamlined. Okay. So, exact accumulation functions. Where do we find them? Where do they come from in the first place? Exact accumulation functions. So what if we're saying accumulation function, what's another way to say that? What are we saying when we say accumulation? Okay. What's that? Accumulation is how fast it's changing? Okay. Yeah. Yeah, so we've been kind of pounding that accumulation is the sum of bits. But you've seen accumulations your whole math career without thinking of it that way. All right? Those are just any kind of quantity function. It's just now that we're seeing those. So like, for instance, the area of a square. Okay? The area of a square. So you've always just seen that as a quantity function. You plug in a side length that spits out an area. In the past month, we've been kind of taking a different perspective on it, that any given area is the sum total of the growth of little bits of change to the area. Okay? But these accumulation functions are just the same as all the quantity functions that you've been dealing with since 7th grade. Okay? But now we can see it this way. So if it's an accumulation function, then it can be written as some integral, right? If it's an accumulation function, it can be written as an integral. All right, another example, volume of a sphere. Okay? So before, you thought of that as just plug in a radius, it gives the formula gives you a volume, and that's totally legitimate. But now we can also see that as, so here's that view of it. Plug in a radius, it gives you a current volume. But we said, okay, but accumulation functions could also be thought of Any given volume was a sum total of lots of changes in volume. Okay, so any function that gives an exact amount of one quantity as a function of another is an exact accumulation function. And therefore, it can be represented as an integral of its exact rate of change function. That should make sense. So there's two ways to look at it. So, and this is kind of what we talked about before. This is the difference between... Oh, that's not what I wanted. This is what I wanted. This is a perfect example of what we call closed form. This is a closed form of this accumulation function because it's just rapid fire. We can spit out volume. You just plug in radii, and it can just spit out volumes. Boom, boom, boom. This is what's called open form. It's reflecting the process of building up to a volume from zero, from a radius of zero, right? A radius of zero up to the current radius. This shows that process of how a little bit at a time that volume grew up to its current volume, okay? So, closed form, open form. Closed form, rapid fire results. Open form reflects process and would require a process to generate a result, okay? So, again, we talked about this. So then any quantity function, now we see it as an accumulation function or an integral of an exact rate function. We just don't know what that exact rate function is, but that's the new journey that we're on. You know the amount that you have, and you want to figure out how fast it's changing. So this is the new journey that we start today. Okay, so hopefully that makes sense. So let's look at the area. Let's just look at the area of a square. Okay, so here's this function, area of a square. Plug in this, so x represents what quantity about the square? X is what? The length of the side, right? Length of the side. And so, so this is why we call raising something to the second power squared. Did you know that? Why do we say x squared when we raise it to the second power? Because it's the radius, because it's the area of a square. Okay, that's where that comes from. All right. So the question is then, we got exact accumulation. What's going to be the first step on our journey from exact accumulation? On the reverse journey. Approximate accumulation. Okay, so I want you to take a minute and think to yourself, what kind of function is an approximate accumulation function? And another way to ask that is, what's its graph like? What's the graph like of an approximate accumulation function? Okay, so we're thinking about this journey we've been on, okay? And then how might we construct that type of function from the exact function? All right, so talk to the person next to you and see what you come up with. What kind of function is an approximate accumulation function? What's its graph like? How might we make it? Not enough people coming to lecture. We need to take attendance. Okay, ideas. So what is an approximate accumulation function? What's its structure? What's its graph like? Adam? He wants piecewise linear. So anybody else? Different suggestions? You agree with that? Yeah.
I agree with that. It's usually an underestimation or an overestimation.
Okay, it's an underestimation. Or if it's approximate, it's an underestimation or overestimation. Was there a hand over here? Okay. Is it a step function?
No.
No. Good. Good. Yes, piecewise linear. Piecewise linear is our approximate accumulation function. Okay, so now we've got this exact accumulation function. So constructing this piecewise linear approximate accumulation is going to be much, much different than how we did it before. Because before we constructed this what? From the approximate step rate function. But now we're building this from this curve, this exact accumulation function. So can you imagine how are you going to construct that? What do you think? How would you construct it? Yes, sir.
I would plug in certain x points.
Okay.
Distance between each other being delta x.
Okay.
I would graph them and connect the points.
He's going to take points on the graph, get actual points on the graph, and then how do you want to connect the points? With what?
Straight lines.
And then connect those points with straight lines. How many people said that when you had your discussion? You're going to have points on the graph and you're going to connect them with straight lines. Nice and high. I just want to know. Not bad. Okay, yeah, that's exactly right. Okay, the line segments whose endpoints are points on the curve. So it looks like this. So do you see that the y values of this new approximate accumulation are trying to be like the y values of the exact one, right? And so it wouldn't make sense to do a step, horizontal steps. That just doesn't make sense. We're trying to make it be like the curve as much as we can. But then what is the quality of this that's going to help us with the mathematics? So what's the quality of the piecewise linear graph that's going to help us make the mathematics simple? Constant rate of change. It's the same things before, right? Constant rate of change. Okay, but then we're going to have a different constant rate for each interval. Okay, and so then what are my intervals here? So I'm choosing intervals, delta x intervals of 1 unit, whatever the unit is for my square side length. Okay, so what about smaller intervals? What will the effect? So we can do smaller intervals. And then we still have a constant rate of change over each interval. What's the effect of that, doing that? Yeah, do you see that this approximating function is hugging that curve a lot better, right? Its y values are going to be a lot better to that curve, right? Okay, so we're going to write it. So we're going to write this for this function, this area function. Can we write just for, say, from just the first 4 pieces from 0 to 2 with a delta x of 0.5? So what's the deal with the constant rates? So the way we define these constant rates, we say in each x interval, the linear piece achieves the same change in y as the function does. Okay? So if I just I'll pick this interval right here from 0.5 to 1. Delta x is 0.5, and that's the interval we're looking at. And so what happens? We're going to get that constant rate of change such that the amount that the function changes, the value of the function, the output, is the same for our linear piece as for the actual function. So this right here, this is delta y. We want that delta y to be the same for our new linear piece as it was for the old function. And that's how we're going to define that constant rate. So that delta y is the same. So this new segment that we're creating as part of the approximate function will have the same change in y as the function did in that interval. Doesn't make sense? Okay, so
going from 1 delta x or 0.5 to 1 and just measuring the height of delta y, the change in y.
That's how we're going to get that constant rate. See, because we're going to need to make this piecewise linear function. We're going to need, what is that constant rate, say, for that interval?
Right.
So to get that, we want the segment whose change in y is the same as the change in y of the function over that interval. Okay, so we're going to do the first 4 pieces of this, okay, with delta x of 0.5. Who has learned something in the last month? Can you do it? All right, so you're going to need your function. You're going to need delta x is 0.5. And we have when the Side length is 0. What's the area? 0. Okay, so before you start working on this, you should confirm that you know what is the structure going to be the structure of each piece of this, and then you're ready to start figuring out how to form each line then. Okay, so first question, what's going to be the structure of each individual line of the piecewise function? And then you can get into the guts of figuring out what each one is. All right, so you take 5 or 10 minutes to do this. Go, see if you can do it. Yeah. Piecewise linear, is that going to work? Yeah. Make sure you know the structure, what you're going to use for each line first before diving in.
Will you use
That was 0.5. Okay.
because that's what something to do it. You have 0.00 and you have 5.
Yeah, but you can't. So area of point. This is area of 0.5. You can't use. First of all, there's no F function, right? So we've got
Right.
We've got area, the function area, and the function capital A. We've got approximate area. But yeah, so this is 0.05.
So basically, find a slope.
You're going to need the slope. And then what's the structure of each line going to be?
So the structure of each line is going to be just one slope.
What do you think?
Oh.
Then what about the structure of each line? What's the overall structure of each line that you're going to write? Yeah. So just see if you can get that first sample. Get the first sample.
You have area. Like this. Area minus 0. So it becomes
got to get these. How are you going to get this rate?
I
It's
just,
not 0.7.
I just don't know.
Okay, even though it's an approximate accumulation function, we're not estimating anything. We're going to find everything that will be exact in terms of what.
Okay.
Everything we write down will be exact values that form the approximate accumulation function. So you're not eyeballing anything. Okay, lots of good progress. And what do you get when you do this? 0.5? That turned out to be 0.5? Not 0.7. It's not 0.7. It does matter. What do you mean? 0.7? Where does 0.7 come from? This is 0.25 minus 0 over 0.5. So that's a half.
Dividing by half, you basically just double it.
Yes. Yes.
It's
Okay, next segment. Next segment. So we need. So let's do this part first. Remember, we used our starting point. So what's for this second segment? We need the coordinates. That's going to be our AB, the coordinates of that point. What's the x coordinate?
X minus 0.
Okay. How do we express, or how can we write the y coordinate of that point?
A of, yeah.
So you kind of have some choices here. Because we've already established what a of 0.5 is from this function, we could use this, or we could use this function. It doesn't matter. We could use area of 0.5 or a of 0.5 because a of 0.5 is determined on the previous line. So we'll kind of follow what we've done in the past, and we'll say a of 0.5. That's fine. So now the question is, how do we calculate that K2, that constant rate of change in that interval?
So area of 1.
So it's going to be final value of area
So it's just going to be
minus starting over. So that's delta y. And we're getting delta y by picking off these function values off our exact accumulation function. So I'm using area. So it's the y value final minus the y initial over, and that's delta y over delta x, 0.5. So that's going to be 1 minus 0.25
So 0.75
over 0.5.
1.5.
So the constant rate here is 1.5. And that's going to be from 0.5 to 1, including 1, but not including 0.5. Yeah, so we can. So that maybe the hardest part of this is getting these constant rates, but we see that if we've got the exact accumulation function, and that's how we're picking points off of that and joining the lines. Well, then we have all the y coordinates of those endpoints by the output of the original function. And so we can get the change in y for each one. Okay, so just to check your work, I think the next one ends up being 2.5. And our starting point is 1, a of 1. So you could write 0.25 here. You could write 1 here. That's totally legitimate. So this is from 1 to 1.5, inclusive. And then if you do the same thing for this last interval, delta y over delta x, using the function, you get 3.5. Questions on that? Did you guys get it?
Yeah, that's a question.
Sure, please.
All right, by adding let's say we have that 3.5 is the fourth line.
Fourth one, okay.
Yeah, 3.5 plus x minus 1.5
Right.
plus a of 1.5.
Right. That's our A, B, right? That's our starting point. That's this point right here, 1.5 and A of 1.5.
It seems to me that it's compound adding, but again, I'm most certainly wrong. Explain why.
Well, so this is calling on our own function to do A of 1.5. When you plug 1.5 into this, where's it going to go?
It's going to go right there where if we can a 1.5 makes a line.
No, it's got to figure out if it's going to add A of 1.5 in this computation, it's going to say, oh, I'm going to put 1.5 in here, and where's that going to take you to get A of 1.5? The third line, which we already established. It's already there, so we're fine. It's the recursive idea, right? And then in that line, it's going to need A of 1. Well, A of 1 is going to take you to the second line. So yeah, so that it's recursive. It's okay because by the time we're writing this line, we already have what A of 1.5 is in the previous line. Other questions? Okay, so now we're going to have some fun. Ready? Now we're going to do this in one, just like we did before. Instead of a bunch of pieces, we're going to write out AX in one rule. One rule. Okay, here we go. We're going to write it as one rule. So we're going to think about, say, we're going to take this interval right here, from here to here, as just any interval in an approximate rate function that we're picking, we're creating. So this is the idea of arbitrary. Okay, arbitrary just means any. You pick any, and it represents all of them. So arbitrary means any single example representing all of them. Okay, I kind of just made it on the spot. How's that they're grading over there? So our interval. So when I say we're picking an arbitrary interval. An arbitrary interval means we're going to pick one. It's going to be a single interval, but it's going to represent any possibility. Okay? So we're coming along here, and we think about our x continuing, and so, boom. We have the current value of x, just like we did before. So we want to write the equation of this segment right here. So we've got a current value of x. Here's our delta x. And we want to write AX now just as one line right there. Boom. And we can do it. We got all the tools. So I want to see what you guys can come up with on your own. Again, first thing you should do is say, well, what's the overall structure of that going to be? What's the overall structure of an arbitrary segment as part of our approximate accumulation function? What will the overall structure be? And then you start working little by little at what filling in the blanks, right? Filling in the blanks. So first decide the overall structure, and then start working on the details. See what you can come up with. See if you can do it. You've got everything you need. You will feel so proud of yourself if you can do this by yourself, and some of you will be able to do it. What's the overall structure? First, make sure you get the overall structure first. Yeah. So we're going to call the exact accumulation function f, okay? So make it easier. So the curve, the red curve, is our exact accumulation function. We'll call it f, just to make life simpler, okay? So f is your exact accumulation function, and you're going. Okay, if we're focused on one arbitrary interval, and we want the structure of how to write the equation of that line, well, so like in this one, wouldn't it be the same structure as you had in the previous one for the second interval? Okay, so what's going to be the structure of a segment in an arbitrary interval? Y equals what? Yeah. Point slope form. It's point slope form. It's the same thing we're doing before. Now we're just making it general for all intervals. Every interval was point slope form before. So now one interval will be point slope form. Okay, so that's your structure, point slope form. What'd you say? Why would you do that? Because? That's right. Some of you are starting to get it. It's going to click. You can do it. I'm going to get coordinates A, B. If you get coordinates A, B, then you can get the coordinates at the end of the interval, and then you're home free. Yeah, delta x is a distance, it's not a one coordinate. So we need a single coordinate that's the left side of this number. How can we get that x value? That's the left side of the yeah, but you don't know how far that is, right? So you need it to work for any x in that interval. So with any x in that interval, we'll give you the starting x value of this interval. Well, that's going to be the y coordinate. What we have that gives us the x value at the start of the interval. So here we go. You might have it. That's the key. If you can answer that question, the whole thing just falls out. You can do it. Use the function. So we need point slope form. So So then we need two things. We need a, b, which is this coordinates of this thing. And then we need the rate of change. So work on the x coordinate of this point right here. You get the x coordinate of that point, and express it, then the whole thing falls out. What is the x coordinate right there? Who remembers? So what's the y coordinate? What's b? So what function are we creating out? F is the, we're getting the y coordinates, right? So now what's the, what are the coordinates of the and the interval, right? We're going to, so AB gives us the AB, and then we need the rate of change. Don't just write them. So this is that, this is left. What's that?
Let's say that everyone's
This is fixed, this is constant. X is increasing, so no matter what X is in this interval, we need something that tells us that coordinate, no matter what X is. The form X minus, you need A, B, and you need K. You always leave, no, you always, you need the coordinates of the point, and you fill them in there, and you need the rate of change. Look at your previous function. They're all x's here. That allows for x to change in the interval. Okay, and what's b going to be? It's not a. It's not a. Where is b coming from? No, it's the y coordinate. It's the y coordinate. You can't use you can't use its function to explain itself. Almost. Almost. You got the right idea. We need to nail down the coordinates of this point and the coordinates of this point. You didn't quite do that, so you kind of jumped into this a little too quick, but you got the right idea. But we got to get the coordinates of this point and the coordinates of this point. Okay, so thank you. Thank you. Thank you. All right, here we go. So here's the key that gets you started. As x increases through these arbitrary intervals, so now it's in this interval. Okay, this could be any interval. This could be the 2nd, the 10th, the 20th interval. It doesn't matter. As x increases through that interval, we need to get that. So we can get a, the coordinate, the x coordinate of that point. So, but x is changing. So we need something that no matter what x is in this interval, it gives us that. And we have it. What is it? Not x minus.
The y value? It's left
What's the x value at the start of this interval, no matter what x is?
of x.
Left of x. Left takes an x value and gives you what? It gives you the x coordinate at the start of the interval. So if this is, so we got our x coordinate is left of x. What is the y coordinate of that point then? It's the y coordinate on the red exact graph, which comes from, y coordinates come from f. F of, keep going. Go, keep going now. Your next, so you just got that, we just got that and that. We're done with that. So that's our left of x. That's f of left of x. What's left is the constant rate of change. And for that, you're going to need this coordinates of this point. Don't use right. Don't use right.
Don't do it.
Don't do it, he says. Keep using left.
I think he's got it, Professor.
No, just get the coordinates of that point. Do you understand that the coordinates of the first point are left of x? So work on the coordinates of the second point. You're done. You just plug everything in. Just work on the coordinates of the second point. That's all. Just, you can do it. What's the x coordinate? And what's the y coordinate? If this is left of x, then what's that x coordinate? Besides right of x.
That wouldn't be left of x
Plus,
delta x, yes.
and so then the y coordinate would be?
And the y coordinate would be f of left of x plus
That's it.
You get 2 delta x.
Yeah.
Alright, so for the second coordinate,
Yeah.
x coordinate is going to be 2 delta x. 2 delta x.
Because this could be any interval. This could be the 10th interval. This could be the 20th interval. So you can't do 2 delta x. How are you going to get it? You got, this is left of x.
Right.
So then what's that? How much farther are you going?
Plus the delta x.
And then what's the y coordinate?
That would be the same thing, left of x plus delta. Oh, I'm sorry. No, f is, yeah, f is.
Take that x coordinate, put it into f. You got it. So now you just write down everything.
Would it be left of delta x? Just left of x. Left of x.
Yeah, that's
I don't want to talk about it again.
I heard it just so left of x.
I don't want to say it again.
Okay, so x coordinate of this point. X coordinate of this point right here. Left of x plus delta x. Okay, so that's our x coordinate up here.
I don't understand this. Are you getting it?
And what's the y coordinate at that point? Yeah, so it may be kind of look complicated because there's a lot to write, but all it is f of that x coordinate, right? Just f of that x coordinate gives you the y coordinate. So we just do f of that whole thing, which I'm not going to have room for. Okay, here we go. Left of
Small, you can have room for it.
plus, still not going to have room. So the left side is left of x, f of left of x. Then the right side, you're just going to add delta x to your x coordinate, and then plug that into the f function to get your y coordinate. So now we've got everything we need. So how can we calculate the constant rate of change in this arbitrary interval? What's the structure of that going to be? The structure of the constant rate k. What will the structure just of the k be? Structures, not delta y over delta x. And how will we get delta y? Final function value minus initial function value will be delta y. And then what will the delta x be? Delta x, right? Yeah, you could do this final minus initial, and you're just going to get delta x. So here we go. I'm definitely not going to have room. I'll do it at the bottom. Here we go. K, so what's K? Delta y? Final value of the function minus initial value of the function over delta x. That's delta y right there. That's the change in y. It's that y value minus that y value over delta x. That's k. K times x minus a. What's a? The x coordinate of that point. Plus b. F. The b is going to be the y coordinate at the left side. F of left of x. So that is true. That will work for every single interval. So as x increases through the intervals, for whatever interval it's in, it's gonna generate that piece. You move into the next interval, and boom, left x changes, and it generates the next piece. X keeps increasing, so it's going to increase. Going to produce all of these constant line segments. All right. Anybody have a question? Please.
Okay, so that's good for the x value for the, let's say this is in a second interval, just for argument's sake.
Okay.
How does it accumulate what's already been in the first interval?
Because this is, see, in the third interval, f of this x value is the total accumulation up to that point. So now that will become the AB. So now when x is over here, f of left of x will be that y coordinate. So it just does automatically. Okay, you're going to miss top hat. Sorry.
This is only for the second interval?
No, this is for all intervals. This isn't for, we build it for one arbitrary interval, but now this is the whole function. It generates every single line segment.
Great.
It generates the first line segment. It generates the second. It generates the third. It generates the fourth. It gives you the whole function, this piecewise linear function, in one rule. It doesn't just give you one piece. It gives you all the pieces. I'm glad you asked that. That's important. Okay, so let's take a look at it. So I've got the slider at, here's exact area, right? There's our exact area function. And we have the approximate area function. And we can think about, oh wow, that's fast. We can think about x increasing, because what's the next step in the process going to be? What's the next step? Now we have the approximate area function that we just did. Okay, and so what will the approximate rate, think about x increases. what will the approximate rate function look like? It's going to be, right, we got our side-by-side graphs. It's going to show up over there. What's it going to be like, the approximate rate function?
Steps.
Ready? So as it's in that first interval, it has a constant rate, so it's going to be a step. In second interval, constant rate, so it'll be a step. So how's this approximate rate function? Pretty good rate of change function? Pretty close? Or not so good? We can do better. How can we do better? Make delta x smaller.
It's like 0.00 something.
Make delta x smaller.
That won't be.
Make it smaller again. For this particular accumulation function, what does it look like our rate function is turning out to be?
Straight line.
Yeah, it looks like our rate function is, for this particular, I'm like a little, something in between here. There we go, that's good. So, very small delta x. My delta x is at 0.04. And you can see now, the approximate rate function is starting to begin to look like maybe it's going to be a line. And so if you imagine that as a continuous, those are steps, really small steps, 0.01 of width. But if you imagine that the delta x getting smaller and smaller, we have the actual rate function, a continuous rate function. Same idea as before. We just want delta x to be sufficiently small enough so that we are convinced that there's no difference, right? It's indistinguishable. So, and indeed, that is the exact rate function. The exact rate function is this straight line. Okay, top hat.